All right, back to work. Let's start taking some look at approximating areas, my minions. Big picture. We're going to break up the graph into rectangles of equal width and approximate the area of each rectangle. And so the sum of these little partial areas will be approximately equal to the entire area. So ideally, you're going to have this. You want to break it up into equal width. We're going from here to here. Maybe we'll cut it in half. We can cut it in half again. This would give us 4 rectangles. Common strategies to do are use the left endpoint for each rectangle. Whoa. What the hell just happened there? We'll use the left endpoint for each rectangle like that. And notice in some areas it's overdoing, some areas underdoing. Like only the blue area is the actual area. Or we could do right endpoints. I could just go up to the right side, make my rectangle like that. Ideally, you want these the same width. And so the way you do that is you count up how many you want to make. Let's say you want to make, like I just did there, I want to make 4. This width is B minus A. So I got a width of B minus A. I have 4 rectangles. So I can divide this by 4. Okay. That's the general process. We don't know how many rectangles is going to be, and it depending on how we decide it. So we often say the number of rectangles is n. And so when we do it, like each breakup there, we call, let's say there's equal distance, we say each of these is delta x. So delta x is b minus a over n. Also worth noting, the way I'm doing it, I have these points here. I would call this x0. I would call this x1, x2, x3, x4, where this number is n and that starts at 0. It works well for the format we're doing. That tells you how many rectangles you're working at. And it actually tells us what the value is. Like if this is 1 and this is 3, 3 minus 1 over 4 would be 2 over 4 would be 1/2. So I know each time I go right 1, I'm going up 1/2. This would be 3/2. Going up another half would give me 4/2, which is 2. Go up another 1/2, I get 5/2, 2.5. This is 1.5. Finally go up another 1/2, and I get 6/2, which is 3. So that's how we are going to use those values in a little bit to help us figure out the area, as you'll see in the pictures coming up, okay? So that's our big picture approach, what we're doing here. Break the area up into rectangles and go from there. We do have a as a low number. I was just walking through to doing x0 through x4. But if we're having n rectangles, we're going to go up to xn. This actually gives a nice little formula for finding at any of the x points. So if I want x3, I is 3 here. I'm going to I multiply by I there. And like x0, even though it's not listed, is plus 0 times delta x. Oh, that doesn't look good. Maybe I'll put that in there, though. In green, what were we writing in green? Plus 0 delta x. And that is plus 1 delta x. Now, with it only being 0, we tend to not write the 0. So since it's 0 times it, that just goes away. And since it's 1, we tend to not list the 1. When we break it up like this, it's called a partition. When you break up a thing into a bunch of rectangles, it's called a partition. And if you make each rectangle the same width, it's called a regular partition. This terminology comes up later in what we're doing. And it just makes it so it's equal width for each rectangle, okay? So when we're approximating areas, there's two main approaches we start with. We do the left endpoint like I was talking about, or the right endpoint. If I'm doing the left endpoint, I wish these had actual values here, but I'm going to write them in since they didn't. This is x0, this is x1, this is x2, this is x3, and that is x4. The actual points on the line are f of x0, because that's the value there, f of x1, f of x2, f of x3. So to get the value of this rectangle, I'm going to multiply by f of x naught times the width. And the width is our delta x. So this rectangle would be f of x naught times delta x. This rectangle over here would be f of x3 times delta x. So that's kind of like what we're doing here. And we're doing each rectangle one at a time. That's by using the left endpoints. You'll notice that even though n goes up to 4, our rectangles only, the x value when we do left endpoints only goes up to 3. So that's why we have the I minus 1 here. That also helps us compensate for starting at 0. And so the approximate area is adding up I equals 1 to n of the height of the left side. That's what this is. Height of the left side of each rectangle times delta x. Okay? I'm going to leave the other coloring in. I think that's helpful for what you're looking at later. We could do it with right endpoints too. Same setup. x0, x1, x2, x3, x4 here, so the n equals 4. Now that endpoint that we need is f of x1. This one is f of x2. That doesn't look good. We've got f of x3, and finally f of x4. So if we're going from I equals 1 to 4, we only need xi for what we're doing. 1, 2, 3, 4 is our endpoints, and we're doing 1 to 4 here. So we just have xi on the inside. Same idea, we're making rectangles. When all of the values are below, I'm going to mention it here because it's kind of brought up later on. When all the values are below the line, this one here, let's go with purple here. This is called the lower sum, which means like the low estimate. And this one here is called the upper sum when we add up the areas, because we've included extra bits of rectangle here, now, right? We've got extra bits of rectangle that aren't in the actual area, so we've overestimated. Whereas up here, we're missing part of our stuff. We're not filling in the entire area, so we're underneath the actual value. So these are just approximates, okay? Now, if it's curved the other way, it actually does, which ones do which are opposite. Maybe I'll sketch that real quick because I don't think I have it sketched below. So if I curve this way and I'm doing left endpoints, I'm overestimating with left endpoints, and so this would be an upper sum. So depending on how it curves, it could be a lower sum or upper sum. Don't just assume left is lower and right is upper. Okay? And if it mixes like it did up here, it's kind of hard to label which one's lower and upper because it changes. All right. Like in this graph below, this is f of x equals 1/2 x squared on 0 to 3. It is broken up into, let's see if we can, that doesn't show up what I just did. 1, 2, 3, 4, 5, 6 rectangles. That's where we got n equals 6. So if we want to find out the width of each rectangle, we do the n value minus the starting value and divide by n. And so what that's telling us here is that the width of each rectangle is 1/2 wide. Okay. Notice you can see how like this is a lower estimate over here. This is below and this is above. So sometimes we include too much or too little. We want to actually calculate the values here though. I write out the formula here. We're doing the lower estimate uses this formula right here. Or the left estimate, I should say. It's lower in this case, but left estimate. We're doing 6 rectangles, so we go up to 6. The lower or the left estimate uses xi minus 1, so we're using the first 5 points here like that. So x0, x1, x2, x3, x4, x5. Each one is put into f, so we get f of each. That gives us our y value for the height. Okay, and then we multiply by delta x. We can factor out delta x, and I think it's a little easier to write everything when you're working on this later on. It's easier to factor out the delta x. So here, factor out the delta x. I mean, we had it on each one, and it's consistent on each one, so we can just factor it out. Okay, then figure out what those values are. So x0 is 0. If I go over 1/2, remember this is the distance we're moving over. If I go over 1/2 from 0, I get to 1/2. If I go over 1/2 from 1, I get to 1. If I go over 1/2 from 1, I get to 3 halves. 1/2 from there is to 2, and then 5 halves. Okay? Then that is it, plugging it into 1/2 x squared. So we're figuring out what those are. 0, 1/4, 1, 9/4, 4, and 25/4 if I square everything. This is my delta x right there. I factored it out. And then what I did is I got a common denominator here. 4 over 4 matches this one. 16 over 4 matches 4. This gave me a way to get it all into one fraction, so it was easier to put in the calculator. And so we get 3.4375. If we do R6, we're doing the right endpoints. So we're doing those. So and I immediately jumped to factoring out the delta x here, but we got the x1, f of x2, f of x3, all the way up to f of x6. And there's my 1/2 from delta x. This 1/2 is from actually the 1/2 x squared. Like there, I factored. So this 1/2 is that delta x. This next 1/2 is this right there. So that goes to there, and all those go to here. And I kind of sped that up on the next line, where I just did the 1/2s right away together. Then this is my f of x1 is 1/2 squared. I'm going through, I add it up, I get 5.6875. That's an overestimate. So L6 underestimated it, R6 overestimated it, and our actual area must be somewhere in between them. Okay? Thankfully, we get past these Riemann sums pretty quickly because they are boring and not fun to do. The following actually shows us how increasing n reduces the error, though. In the following, we have x minus 1 cubed plus 4. So when we do 4 rectangles, L4 is 7.5, R4 is 8.5. And then if we do 8 rectangles, notice that the space kind of gets a little shorter on them. They kind of stretch this graphic out, makes it look a little bit better. But when we add up all these, we get 7.75 and 8.25, which is kind of like bigger than 7.5 and less than 8.5. So it's kind of like L4 is less than L8 and R8 is less than R4. And our area, true area, is getting squeezed in. We jump up to 32 rectangles. Check out this bad boy. Look at how little extra area or under area is done the more rectangles we do. Up here, we had a big old chunk. Here, they're just little tiny chunks. When you add those up, 7.9375, 8.0625. I actually did it on a number line. So like 7.5 is way over here. L8 got us here. L32 was 7.9375. R32 was 8.0625. When you multiply and add this all up. And it looks like the bigger n gets, the more we're squeezing in on what the actual area is. So if we did R equals 64, it might squeeze in even further, get like this. You know, so like we're getting closer and closer to the actual area. It looks like it might be 8. And we could, well, we'll see later on that how we get it, and it probably is 8. I want you guys to give it a try. Find L4 and R4 of f of x equals x cubed on 0 to 2. Okay, if you do that, delta x is b minus a. That is my b. That is my a. So 2 minus 0 over n. N is this value right here, 4. So 2 over 4 is 1/2. The width of each rectangle is 1/2. So I can figure out my x naught values by just adding 1/2 as I advance until I get to my n value. I started with 1. I started at 0. I ended at 2. Picking n equals 6 here sucks because then you can't do a decimal. You got to do a fraction the whole way. I got the hiccups. If you do L4, I factored out the delta x. Remember, we're using left endpoints, so f of x0 through f of x3. If you go through the math, you should have got 9/8. R4 is the same setup, but right endpoints. So rather than using 0, 1/2, 1, and 1.5, we used 1/2, 1, 1.5, and 2. And we cube each of those, and we ended up getting 25/8. That's it for this video. Got one more. The next one's pretty short. Peace.